we discussed a very simple function which was introduced by Euler, and this is the zeta function. The reason for introducing the function, I explained, was it was a way of trying to sum up inverse powers of an integer. People had already found out how to sum up 1 plus n plus 1 plus 2 plus 3 like that, or 1 plus 2 squared plus 3 squared, and formulas for those are available. So it was natural to consider functions 1 upon n to the power of k summation over n. And this was the kind of function which Euler considered, but what he did was he did not stop, he went from 1 to infinity. So this is infinite sum. So this would be 1 plus 2 to the power of k, 3 to the power of k, like this, without end. This function of Euler was generalized by Riemann where he replaced k, which is an integer, by s, a complex number. What we showed last time was that zeta of 2, that is when k is equal to 2, which is 1 upon n squared 1 to infinity, this was equal to pi squared over 6. We did not prove this, we just stated this result. On the other hand, we showed that this was equal to 1 upon p squared product, which means this is 1 upon 1 minus 2 squared, 1 upon 1 minus 3 squared, 1 upon 1 minus 5 squared, and so on. So what you're doing here is you're taking these terms, and p is a prime. You're taking the product of the primes. And what I emphasized was this is an extraordinary result. On the left hand side, you have pi squared over 6, and on the right hand side, you have just prime numbers. Now pi squared over 6 is something which is present in the real world. The pi is related to the circumference of a circle of radius r is 2 pi r. The area of a disk of radius r is pi r squared. So pi is something which you can measure, and it's a real world object. Whereas on the right hand side, you have just prime numbers. So this is an astonishing link between the prime numbers and something which is in the real world. Since this is a significant result, I thought I will spend a fair amount of time today working this out and show you how this is pi squared over 6. In order to do this, I will have to introduce one of the great ideas of mathematics, which is called the Fourier series. You see, when we first started these lectures, at the very beginning, we wrote down that the number, any integer n, could be written as ak 2 to the power of k, ak minus 1, 2 to the power of k minus 1, a0, 2 to the power of 0. So we call this is a base 2 expansion of any number, and it is used in computers all the time. So this is called base 2 expansion. So it tells you that any integer can be written in terms of a fixed integer. In this case, n is an arbitrary integer and 2 is a fixed integer. Instead of 2, we can put 3 or the more familiar 10. Then we have a base 10 expansion, right? For someone with great imagination, they might ask the question that if I move away from integer, if I move to functions, f of x, so this time a function means I have a number which depends on another number. So each time I give you a value for this number, which I take it to be a real number, x is a real number and f of x is a real number. Right. Now we have a function defined. The function is for each time I give you 1, I get one number. If someone is extremely imaginative, they might say that if I think of f of x as my n, can I write any function in terms of powers of a fixed function? Okay? So for example, can I write f of x, can we write f of x in terms of powers of a fixed function? Here we have one integer and we've written it in terms of powers of a fixed integer. So I want to ask, can I write f of x in terms of powers of a fixed function? Okay? So this thing, for example, okay, but this time I have done something different. I have made the thing more general. Here we had a finite number and we had a finite number of terms here. So a function depends on a real number. A real number has infinity of possibilities. So for example, if I just look at the, it can be half, 1/3, 1/4, 1/5, or it can be any real number which is not necessarily a fraction. So the infinite number of possibilities. So that means that this thing has infinite amount of information in it. To capture that, we want to write an equality in which this thing does not end, it goes up to infinity. So this is one example. Another example is f of x So I have not written powers here, but I have written the function in terms of coefficients a0, a1, a2, a3, a4, no end, b1, b2, again no end. These go up to infinity, right? And this is another example. There are many other possibilities. So what we are going to do is to look at this possibility, and this is the idea of Fourier. Fourier presented this idea to the Academy in France in 1807. In front of him were sitting some of the most distinguished mathematicians of the world, Laplace and people like that. And when they heard this, they thought this is a ridiculous idea. It cannot be correct. The reason is that here we have let x be between minus pi and plus pi. It has a finite range. Okay? Why were they worried? Because Fourier said this function can be arbitrary. Arbitrary means that the function might not be given by some simple expression. It could have jumps, it can go up, it can go down, it can be discontinuous. For all of those cases, what Fourier was saying was this kind of expansion is still valid. Okay. It turns out that Fourier's intuition was right, and a lot of the development of pure mathematics at that time was centered around establishing under what conditions this expansion is valid. So this is the representation of a function by another function. On the right hand side, these things are periodic functions. Cosine x, sine x are periodic. That is, cosine of x plus 2 pi is cosine x, sine is sine x. Okay? So these are very simple functions. They're smooth functions. You can differentiate them as many times as you want. But Fourier was saying the left hand side, no matter what it is, can be written in this way. In our example, what we will do is we will apply this idea to this very simple function. So the problem then is, how should these coefficients be found? Okay? And the general formula, which we might prove later on, for the moment we write this down. This is equal to 1 upon pi minus pi to pi x squared dx, which we can prove is 1 upon 2 over pi a n is 2 over pi So these are coefficients calculated using. So let me state this clearly once again. When you are given a function in terms of cosines and sines as a fixed functions, the coefficients depend on f of x. They have to be calculated. Each time I give you a function f of x, you have a method for calculating the coefficients. And the rule for calculating, I've written down. This rule this is sine. And this rule written down, valid for x. So this rule is valid for a function which has the property that if I replace x by minus x, it does not change, because minus 1 squared is plus 1. So this is true, and then it turns out that this quantity is equal to 0. Once more with feeling. If I have x squared, and if you want to calculate the coefficients, then I have to do these two calculations. For when f of x is x squared, all of these terms are missing, which means that those coefficients are exactly 0. That means that b1, b2, b3, all of them are 0 when f of x is x squared. So the ones you have to calculate are the coefficients a0, a1, a2, and so on, right? And the formula for doing that are written down here. So this is a0, this is an. So let us do these calculations. First, we calculate a0. So a0 is equal to 2 over pi integral 0 to pi x squared dx. So that is equal to, this becomes 2 over pi x cubed over 3. So that is equal to So that is 2 over pi into 1/3 pi cubed, which is equal to 2 over 3 pi squared. So we have found a0. Now let us calculate an. Now to do the calculation, we need to know that cos nx dx is equal to sine nx over n, and integral sine nx dx is equal to cos with a minus sign. So these are two results which we need. And to do an integral like that, you do a thing called integration by parts. Okay. So there what you do is this is equal to 2 over pi. The first function you take out, integrate cos nx dx, and then the whole lot you look at the difference. So this symbol f of x a b means f of b minus f of a notation. Okay, so we have this, this is the first term, minus integral there's a 2 over pi outside, 2x sine nx over n dx. So here you differentiate the first function, which gives you this, and you integrate the second, and this whole thing is between 0 and pi. Okay. Now the first term is between 0 and pi. Right. So let's do the first term. First term, which is this term, first term. Second term. So there are two terms, the first term and the second term. So let's look at the first term. So this is then 2 over pi x squared, and this integral gives you sine nx over n. And this has to be worked out between 0 and pi. So when you have the x equal to 0, this makes it 0. When x equal to pi, sine n pi is equal to 0. So this thing, and x equal to 0 means x squared equal to 0. So this thing is 0. So the first term is 0. Now let's look at the second term. The second term. Let's write it again. The second term is minus 2 over pi integral 0 to pi 2x sine nx over n dx. That is equal to minus 2 over pi. Again, I write this as the first function into the integral of the second minus integral of 2 cos nx over n squared dx. So, and this is between 0 and pi. Let us work this out. This I call the third term, and this I call the fourth term. So the second term has generated a third term and a fourth term. So let's look at the third term. So when x is 0, this is 0. So it's only when x is pi, there's a plus sign here. So you get 4, and the pi's cancel, and you have cos n pi divided by n squared. Right. So that is, so when I work this out, I have to first put x equal to pi, and then subtract the term I get when I put x equal to 0. When I put x equal to 0, because of this term, it is not contributing, and there's a minus sign here, there's a minus sign, so I get plus. Now it turns out that cos n pi is minus 1 to the power of n. So this term is equal to plus 4 to minus 1 to the power of n over n squared. So we are left with this term. So this term we can work out as 0 to pi. There's a minus sign outside, and there's a minus sign here, and there's 2 over pi, and there's a 2 from here, and cos gives you sine nx over n cubed. Okay, so I just have to integrate this. When I integrate cosine, I get sine, there was n squared already, I get n cubed, and there was a 2 sitting outside like this. But you see, sine of x at 0 and pi are 0, so this term is 0. Okay, so we conclude from this that an is equal to 4 into minus 1 to the power of n over n squared, and a0 is equal to 2 over 3 pi squared. So in other words, a Fourier series expansion is x squared is equal to a0, which is 2/3 plus summation n equal to 1 to infinity 4 okay. So we have completed the calculation for the where the function f of x is equal to x squared and x is in this range. What we have found is that the Fourier expansion has this structure. The coefficients have been found. The coefficients have been determined from the fact that this is x squared by carrying out integrations. Okay. Now we do a little trick. You see, I want 1 upon n squared, but I have got cosine multiplying it. So what I do is I set x equal to 0. Then what I get is 2/3 pi squared plus summation n equal to 1 to infinity 4 into minus 1 to the power of n over n squared is 0. So I can reorganize this. I can divide by 4, right? Sorry, the a0 which I had, right, there was half a0 plus an cos nx summation 1 to infinity. So what I found was A0 is equal to 2/3 pi squared, but in the Fourier expansion, right, there was a half. So this should be this multiplied by half. So this multiplied by half. Right. So remember, okay. So then what I have is 1/3 pi squared is equal to minus 4 summation minus 1 to the power of n over n squared by setting so this means that I divide by 4, I get pi squared over 12 is minus summation n equal to 1 to infinity minus 1 to the power of n over n squared. Okay, so we've got pi squared, but we have a minus 1 to the power of n floating around. Okay, so I will now claim that this is exactly that formula. Okay, so let us show that that is exactly the same formula. The claim, this implies pi squared over 6 is summation 1 n squared 1 to infinity. Let us prove this. How do I do that? Well, first you notice that summation n equal to 1 to infinity minus 1 to the power of n over n squared is equal to plus summation 1 upon 2n squared 1 to infinity minus summation 1 to infinity 1 upon 2k plus 1 squared. You see, what we are doing here is we are saying this number here can be even or odd. When it is even, when this is 2n here, then the 2n there makes this plus. When this number is 2k plus 1, then this is minus. And so this is like this. So the first term is 1/4 summation 1 to infinity 1 upon n squared minus 1 to infinity 1 upon 2k plus 1 squared. Now let us look at summation 1 upon 2k plus 1 squared 1 to infinity is equal to summation 1 upon n squared 1 to infinity minus summation 1 to infinity 1 upon 2m squared. So what have we done here? Again, we have said this thing has all the even and odd. If I subtract out the even, then I am left with this. So the even terms subtracted out. But this thing is zeta of 2 minus 1/4 zeta of 2. So that means that this term is 3/4 zeta of 2. Now let us go back to what we had here. So this term had a minus sign, so you had minus this thing is equal to summation 1 to infinity 1 upon 2m squared minus summation 1 to infinity 1 upon 2k plus 1 squared So this thing, at the minus sign, this thing is equal to 1 upon 4 zeta 2 minus okay. Right. So this is the formula which we had derived. There was a minus sign outside. I've kept that. Then this thing is, as I showed, that the even part contribution, right, plus the minus the odd part, because the odd part would have a minus sign, right? And then this thing we showed was 3/4 zeta 2, and this is zeta 2, 1/4. So this minus this, and the minus sign is outside, so this is 3/4 minus half zeta 2. So which is equal to half zeta 2. Right? So we finally get so here was our formula. So we have pi squared over 12 is then equal to half zeta 2. So from the calculation which we did there, it is we get pi squared over 12 is equal to half zeta 2. Therefore, zeta 2 is equal to pi squared over 6. So I went through this calculation because the result was quite a significant result. And in deriving this result, we had to introduce a beautiful idea of mathematics, which is you can expand one function in terms of another function. The way this works and when it works and when it doesn't work is a matter of technique. But once you have opened this door, then one can consider many other functions. And this idea of expanding one function in terms of another is widely used in applied mathematics and physics and chemistry and anywhere where people use theoretical ideas. So Fourier had opened the door to all of these possibilities. And in doing this, he had made the subject of mathematics open to a wide range of applications. And for that reason, at the beginning of this series of lectures, I had quoted a letter written by the German mathematician where he said that Monsieur Fourier is of the opinion that the sole purpose of mathematics is to help the natural scientists. He felt, but surely a man of his talent should recognize that the sole reason for doing science is for the upliftment of the human soul. So that's where we'll stop. Thank you.